buffers. Buffer, I buffers are a solution used to keep the pH relatively constant. The common ion effect, which is something we learned back in chapter 23, was actually a buffered solution. A buffered solution right here resists change in the hydronium or hydroxide, which again means the pH stays pretty constant. A buffer is usually made up of a weak acid or a weak base and a completely ionized salt. So a weak acid or a weak base and a salt is what we use to make a buffer. So weak acids include acetic acid, sodium acetate, and then weak bases would include ammonia or ammonium chloride would be some good bases. The acetate ion is commonly used for buffered solutions, which then includes a spectator ion. And this is, again, we talked spectator ions back in chapter 23. It's an ion that does not take part specifically in the buffering, but it is present. It's just there to watch, just like spectators at a sporting event. So here is a balanced equation that we can look at as an example. You can see that the third hydrogen from our hydronium gets added to the acetate ion. That's what is happening while the solution is buffering. The calculations that we will use or that we will do for a buffered solution are very similar to what we have been doing. Here we have Ka expression where we do the hydronium and the negative ion over the original acid. And then solved, we rearrange for that hydronium ion. And we like to solve for the hydronium ion because that then allows us to easily calculate pH. So here is an example. I'm going to start with writing out the chemical reaction. So we have acetic acid and sodium acetate. Which is going to give us the hydronium, the negative ion, so the acetate, and we have the sodium ion as well, but it again is just a spectator ion. So if we write the Ka expression, we have the hydronium, the negative ion over our original acid. Okay, so now we are going to add in everything. Oops, I didn't really want to make that bigger. I just wanted to scoot it down. We're going to add in the information given to us in our problem. So 0.5 molar, right? Moles per cubic decimeter is molar of our acetic acid and our sodium acetate. So 0.5 molar acetic acid and 0.5 sodium acetate. And then we know our Ka is 1.75 times 10 to the negative fifth. All right, so the hydronium concentration is what we want to solve for first, and then we will use that to calculate pH, because pH is the negative log of that hydronium concentration. So we want to find the hydronium concentration first, and then calculate pH. Okay, so we know the original acid concentration is 0.5, and we're going to solve for the H3O plus, so that's our X. So the other piece that we need to figure out is the negative ion. And this, again, is just like we did back in chapter 23. The concentration of our negative ion is going to be coming from the salt, the sodium acetate, because acetic acid is very weak, which means it dissociates very, very, very little. Most, if not all, of our acetate ion is going to come from the salt. So we are going to use 0.5 as the concentration of our negative ion. So we are going to, we have all of our known information plugged in. We're going to solve for X. In this case, 0.5 divided by 0.5 is 1. So that means X equals 1.75 times 10 to the negative 15th. And that's our concentration of the the hydronium. Our question asks for pH, so we're going to do the negative log of 1.75 times 10 to the negative 15th. And the pH is 14.76. Okay, let's try the next problem. We have the same stuff, so acetic acid and sodium acetate, hydronium, negative ion, and then our sodium. We are given concentration of our acetic acid, 0.133 molar, and then the concentration of our sodium acetate, 0.215 molar. Determine the pH. So again, we're going to solve for the concentration of the hydronium. To write our Ka expression. Plug in everything that is given. Hydronium is our X, that's what we're solving for. The original acid is 1.33. And again, the concentration of our acetate is going to be pretty much the same thing as the concentration of that salt. So we plugged in everything that we know. Now we are going to solve for X. Times 1.33 divided by 0.215. So X equals 1.08 times 10 to the negative fifth. Again, that's our hydronium concentration. To find the pH, we have to do the negative log of that. And our pH equals 4.97. That is really hard to see. Okay. Okay, I definitely made a mistake up here. Really kind of minor, because I wrote the Ka wrong. It's the negative fifth, not the negative 15th, which means all of those are to the negative fifth, and that changes that by a factor of 10. So my mistake, but now it is correct. The next problem I did just fine. Okay, let's do number 2. This time we do have some different stuff. We have blood, which is an excellent buffered system. Our pH of our blood stays very constant. And that's what we are calculating the pH of a blood sample. We are given the starting concentration, 0.00134 molar, and would be our spectator ion, 0.025. The sodium is. This is the sodium. That's our salt. So Ka expression, hydronium is the negative ion over the original acid. Okay, Ka is 4.37 times 10 to the negative 7th. The hydronium is what we are solving for. The concentration of our negative ion is going to come from that salt, so 0.025, and then the concentration of our original acid on the bottom. So these ultimately end up as a little bit of algebra because we are solving for X. 4.37 times 10 to the negative 7th times 0.00134 divided by 0.025. So X equals 2.34 times 10 to the negative 8th, which is hydronium. To calculate pH, we will do the negative log of our hydronium concentration. So our blood, or this blood sample, has a pH of 7.63.